Hello friends, I welcome you in lecture number 11 on logic. In previous two lectures we have discussed about logical equivalence and we have seen how we can show that two compound propositions are logically equivalent using truth table. In this lecture we are going to write or understand some standard logical equivalences, and for that we will first understand that a proposition which is always true can be denoted by letter T, and a proposition which is always false can be denoted by capital F. So in writing all those standard logical equivalences, we will understand this thing, that capital T denotes any proposition that is always true and capital F denotes any proposition that is always false. So we will understand meanings of capital T and F in this way when we are writing all these logical equivalences which are standard laws of logic. So first one is identity laws. So identity laws says that suppose I consider AND operator between some proposition P and capital T. Capital T means a proposition that is always true. Then this is always equivalent to given proposition P. This we can simply understand using truth table. Suppose I consider proposition P, then there are two possibilities, either it is true or false, and capital T in this case is that proposition which is always true. Therefore we consider truth value T for capital T. And if we consider AND operator between P and capital T, then we know that this compound proposition is true when both are true, and it is false if at least one is false. And we can see the columns corresponding to P and T and small p agree. Therefore we have this identity law that P and capital T is equivalent to small p. Now whatever laws we will write either for AND operator or OR operator, we can write the another law corresponding to another operator. Here this is for AND operator, so we can write down the corresponding identity law for OR operator in this way. Here I will write P, AND will be replaced by OR, T will be replaced by capital F, and this is equivalent to small p. So we will write only one law, and other law we can write simply by replacing AND by OR by AND, and T by F or F by T. So these are the identity laws which says that P and true proposition is equivalent to P, and P or false proposition is also equivalent to P. This also we can understand or we can prove using truth table, which we did for this one. Second form is domination laws. So domination laws means suppose I consider P or capital T, then again we can use truth table to understand the equivalent statement or proposition to this P or T. So suppose I consider for P I have two possibilities, true and false. This is always true, and OR operator says that if at least one is true, then this compound proposition is true. So here both are true, therefore this is true. Here T is true, therefore this is true. And if we compare the columns corresponding to these two, then they are same. Therefore we can say that this is equivalent to capital T. That means capital T dominates this proposition P, therefore it is called domination law. And To write down equivalent domination law, we will replace OR by and T by capital F, and here I have this another domination law, and another law is idempotent laws. Idempotent laws says that if we consider P or P, then that is always equivalent to small p, and similar statement is P and P is also equivalent to small p. You can again verify these two idempotent laws using truth table. Then we have double negation law. Double negation means, suppose we are considering negation of some proposition P, and if we take negation of this negation, then that is equivalent to proposition P. All these laws can be proved using truth table as we have done in earlier lectures. Then we have commutative laws. So suppose I have two propositions P and Q, then P or Q is equivalent to Q or P, and same thing for AND operator, P and Q is equivalent to Q and P. So these are the commutative laws. Associative laws. So first we write for OR operator. For associative law we require three propositions, say P, Q and R, and here I am taking P, Q in the bracket, or P or Q or R, and these two are always equivalent. And we can write associative law for AND operator also, P and Q and R. Then we have distributive laws. So first we consider distribution of disjunction over conjunction operator, P or Q and R, and this is equivalent to P or Q and P or R. We are considering P or Q, then AND operator in between, and then P or R. This is called distributive law of disjunction over conjunction. Similarly, we can write another distributive law of conjunction over disjunction. So here I am replacing OR by AND 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 by OR. This is equivalent to P and Q or P and R, P and Q or P and R. And if you see lecture number 9, in lecture number 9 we have proved one of the two distributive laws. Then we have De Morgan's laws, that also we have proved. De Morgan's laws are negation of P or Q is equivalent to negation of P and negation of Q. Negation of this disjunction is equivalent to conjunction of negations of P and Q. Another De Morgan's law is negation of P and Q is equivalent to negation P or negation Q. That is, negation of conjunction is equivalent to disjunction of negations. And then we have absorption laws. Here we require two propositions. Suppose I have P and Q, and I am considering P or P and Q. So this Q will be absorbed by P, and this is equivalent to small p. So here we have P two times and Q single time, so Q will be absorbed, and you can remember in this way. Similarly, we have P and Q, that is also equivalent to P. So these are two absorption laws. Then we have negation laws. Suppose I combine P and negation P by OR operator, then this is always equivalent to capital T, that is a statement which is always true. And if I consider AND operator between P and its negation, then that is always equivalent to proposition which is always false. So these are the standard laws of logic, and you can see they are all similar to the laws which we study in set theory. We are familiar with this commutative property of sets. A intersection B and B intersection A are same. So we have similar property here also, commutative property. P and Q is equivalent to Q and P. Similarly, for union also we have this property. If I replace this intersection by union, then I have similar property in logic also. So all the laws which we have in set theory, we have written all those laws for this logic also, and they are all valid. We can use truth table to check their validity or to check their logical equivalence, and we will use all these laws in upcoming lectures whenever it is required. We have some another logical equivalences which involve implications or conditional statements. This we have proved in earlier lecture. In lecture number 10, we have shown that this conditional statement P implies Q is equivalent to negation P or Q. And here this P implies Q is equivalent to negation Q implies negation P. So all these are equivalences or logical equivalences. Similarly, P or Q is equivalent to negation P implies Q. P and Q is equivalent to negation of P implies negation of Q. And all these are just for information. We don't have to remember all these things. We will remember this logical equivalence that we are going to use frequently in upcoming lectures, that P implies Q is logically equivalent to negation P or Q. Similarly, if we have biconditional implications, then we are going to use this logical equivalence sometimes in upcoming lectures, that P if and only if Q is equivalent to P implies Q and Q implies P. And we know that P if and only if Q is true if P implies Q and Q implies P. So that is easy to remember, and these are other logical equivalences that we can prove using truth table. And we will stop this lecture by ending with this note, that if P and Q are logically equivalent and Q and R are logically equivalent, then P and R are also logically equivalent. In symbols we can write in this way: P is equivalent to Q and Q is equivalent to R implies P equivalent to R. So in this way we can prove all these laws of logical equivalences using truth table, and we will remember these standard laws, and we are going to use them in upcoming lectures. So this is all about this session. I hope you like it. Thanks for watching.